Okay, so today we're going to talk about surface area of parametric surfaces. So let's consider that we have some parametric surface. It's going to be R of UV. It's going to be the same as what we did yesterday. X will be in terms of U and V. Y will be in terms of U and V. And then Z will be in terms of U and V. And we are going to suppose that R is a parametric representation of some surface S. So the objective today is to figure out how do we calculate the surface area of that surface S. So R is some region that's defined in the UV plane. Let's just suppose that D, the region that U and V is defined on, is a rectangle. Now what we normally do is we split this up into pieces. And then you choose some point. Let's just suppose that I'm going to choose the lower left-hand point of this region here. I'm going to call that point U of I star and V of I star. That region is R of IJ, so that refers to that specific region. This part then is delta U. This part is delta V. Okay, so then R is the representation, the parametric representation of some surface. So let's say that S is this surface here. So then what we would do is we would take where R is defined and we would map it up onto S. So we're going to split S up. We're going to find the corresponding rectangle. So this is the same one that corresponds to the one on the left that I picked. Again, we're going to choose the same point. This time I'm going to call it P of ij. And the little piece itself is going to be S of ij. So those are labels that we need to figure out surface area. So R of ij is the patch in the UV plane that corresponds to the patch S of ij that has the point P of ij. P of ij is R of U of I star, V of I star. With me so far? We get all my notations? Okay. So we're going to find the tangent vectors at our point P of ij. Hopefully you remember from yesterday, there's two of them. I can find R of U and I can find R of V. So this will be R of U at the point U of I star, V of I star. This is R of V at the same point. So ultimately with surface area, we want to know the area of this little region S of ij. So we're going to approximate it. So we are going to approximate the area of S of ij using vectors, plus U. So the area of S of ij is approximately equal to, okay, area using vectors, area of like a rectangle or a parallelogram, let's say. Cross product. the magnitude of the cross product specifically. Okay. Oh, these are stars here. Sorry, put a star on those. So these two put stars on. Okay, so it's going to be delta U, R of U star, crossed with delta V, bless you, R of V star. Bless you. Wow. Are you all good, everyone?
There's something in this room.
Okay, thank you for sharing. Properties of cross products, I can pull the delta U and the delta V out. So this is really R of U star crossed with R of V star. The magnitude, delta U, delta V. So what this becomes then is that the area of S as a whole is approximately the sum from I equals 1 to M, J equals 1 to N, and then R of U star crossed with R of V star, delta U, delta V. Yes?
Why do you have the underline under? Is it
Just to show you I'm pulling them out.
Oh, okay.
It's just when I was referring to them. Okay, so this leads us to our definition. So that was basically like the Riemann sum for surface area. Here's the formal definition. If a smooth parametric surface, S, is given by that equation we wrote at the top, the R1, R of UV equals X of UV times I, add Y of UV times J, add Z of UV times K, then the surface area, which is generally labeled A of S, you should be able to tell from here. Double summation becomes a double integral over the region D. This is exactly how it appears. So the magnitude of R of U crossed with R of V, and then dA. D is in terms of U and V. So U and V are elements of the region D. Questions before we do an example? Okay, let's do an example. We are going to find the surface area of a sphere of radius A. Okay, in order to do that, based on this definition above, we have to have a parametric representation. So what we're going to start with is we need a parametric representation for a sphere. We did that yesterday. So yesterday, this was number 3A. We used spherical coordinates. X, we said, was A sine of phi cosine of theta. Y, we said, was A sine of phi sine of theta. And Z, we said, was A cosine of phi. We also said how we defined our parameters. So this is the notation. D is all the points phi comma theta, where phi was between 0 and pi. Theta was between 0 and 2 pi. Okay. Are we good so far? So we are going to have to take the derivative of r with respect to u In this case, either phi or theta, and then the other one as well. Okay, so I chose to do phi first. So this will be a cosine of phi, cosine of theta. This will be a cosine of phi, sine of theta. And this one will be negative a sine of phi. Then you're going to take the derivative with respect to theta. So we get negative a sine of phi, sine of theta. A sine of phi, cosine of theta. 0. Okay. Do we follow me so far? Yes. Okay, when I cross them, does it matter which direction I cross or which one I put first? So is RU cross RV the same as RV cross RU? Are they the same? No. What is the difference? Signs. Does it matter then if I choose what order I choose here? No, because you're going to take the magnitude. Okay, so it doesn't matter. I chose to do phi crossed with r of theta. Okay, so I get 0 minus this product, so that'll end up being 0 minus negative a squared sine squared phi cosine of theta. I'm going to write all the terms so that we don't lose anything. If I ignore this one, again we get 0 minus a squared sine squared of phi sine of theta. And then this way, I'll get a squared sine of phi cosine of phi cosine squared of theta minus a negative a squared sine of phi cosine of phi sine squared of theta. You all are checking me, right? Not just blindly copying down what I wrote? No, we're just blindly copying? It's dangerous. What happens if I do the whole thing wrong? If we get it wrong, we're doing it again. So it would be in your best interest to check that I'm doing this right. Okay, we get a squared sine squared of phi cosine of theta. And then we also get a squared sine squared of phi sine of theta. Here, hopefully you can tell those two will be factored out, and you'll be left with cosine squared plus sine squared, in which case you get a squared sine of phi cosine of phi. Now we have to take the magnitude of this vector. Okay. So we're going to end up with a to the fourth sine to the fourth of phi cosine squared of theta. Add a to the fourth sine to the fourth of phi sine squared of theta. Add a to the fourth sine squared of phi cosine squared of phi. Okay, if we look at these first two terms, if you factor a to the fourth sine to the fourth of phi out, you'll end up with cosine squared of theta plus sine squared of theta. So that'll be 1. So we end up with a to the fourth sine to the fourth of phi. And then we still have that other term. You guys follow me so far? Okay. In this case, I can factor out a to the fourth sine squared of phi. And when I do, I'll get sine squared of phi plus cosine squared of phi. This is just 1. So if I take the square root, I get a squared sine of phi. Okay, so then finally we can set up our integral. This is going to be a squared sine of phi. And then we have d phi d theta. Hi. Oh, he's coming. Max, you have a visitor. Thank you. Okay, phi is from 0 to pi. Theta is between 0 and 2 pi. Okay, what's nice about this integral is we can split it up. So I'm going to take a squared out. And then I have the integral from 0 to 2 pi of d theta. And then I have the integral from 0 to pi sine of phi d phi. Which is going to be a squared times 2 pi. This will be negative cosine of phi from 0 to pi. Hopefully you can tell that that's going to be 2. So our surface area ends up being 4 pi a squared. Was that a surprise that that's the answer? Why not? Yeah, of a sphere. Yeah, that's the equation for the surface area of the sphere. 4 pi r squared. Nope, that's news to us. Okay, great. Well, now you know. It was not supposed to be a surprise. Okay, do we understand the process? Okay, not every problem is going to be that long. Okay, I just wanted to show us the possibilities. Okay, one more. Okay, so now the question is, what happens if we have a surface that's z equals some function of f and y? Some function of x and y. So what happens if you're not defined parametrically? Well, we should be able to tell that you can define this parametrically. How could I define this surface parametrically? Sure. How about x equals x? Okay, well, I do. Okay. Y equals y. Okay, so then we're going to do the same process as before and see what happens to the integral. We would take the derivative with respect to x, and that would give us 1, 0, and the derivative of f with respect to x. For r of y, we would get 0, 1, f of y. So then we would take r of x and cross it with r of y. In which case we get 0 minus f of x, so negative f of x, f of y minus 0, but then flip the sign, and then 1. Okay, so then we would have to take the magnitude, which would end up being the square root, partial with respect to x squared, add partial with respect to y squared, add 1. So then the surface area formula becomes the following. Area of our surface is going to be the double integral over the region D of this, although I'm going to define it differently, or write it differently. It'll be 1 plus the partial of z with respect to x squared plus the partial of z with respect to y squared dA. Okay, we're going to do one example together. Find the area of the part of the paraboloid z equals x squared plus y squared that lies under the plane z equals 9. So we're going to use the formula above. So it's going to be the double integral over the region D, which we can figure out later. Square root of 1 plus partial of z with respect to x, so that's 2x squared. Partial of z with respect to y, so that's 2y squared, and then dA. So this simplifies to the square root of 1 plus 4x squared, add 4y squared, dA. Our region D is going to be the intersection of our paraboloid and our plane. So in this case, the circle x squared plus y squared equals 9. What does that suggest to us might be a good idea? Polar. So this will be 1 plus 4r squared. You have to remember when you're converting to polar, you get the extra r. And then dr d theta. R goes from 0 to 3. Theta goes from 0 to 2 pi. And we just integrate like normal. This one we can split up, so we get 0 to 2 pi d theta, and then 0 to 3 of r times the square root of 1 plus 4r squared dr. First integral will give us 2 pi. If you think here of having u is 1 plus 4r squared, our du then would have been 8r dr. We're missing that 8, so we need a 1/8. That'll be to the power 2/3, 3/2 rather, so we need 2/3. Are you okay if I just tell you what the final result ends up being once you plug everything in? Okay. Ends up being pi over 6 times the quantity, 37 root 37 minus 1. Okay. Questions on surface area or parametric surfaces?